Okay, remember this thing? That mysterious chart of boxes from chemistry class? Of course, it's the periodic table. It lists all the known elements, like hydrogen, gold, calcium, aluminum, and even down here, Einsteinium. And what makes an element unique is the number of protons each atom contains. We call that its atomic number. The table starts up here at 1 and keeps going and going and going, but way down here, it just stops. What's up with that? Why can't we just add more protons to an atom and build new elements? Well, correspondent Carla Wall has found some folks who spent their lives trying to do just that.
Every atom in the universe was born in fire. Oxygen, iron, neon, copper, carbon. The fundamental building blocks that make up all matter, all things, were created with immense heat and pressure. By the Big Bang, stars, or sometimes by scientists like Ken Moody.
I don't feel very stellar, I guess.
He does, however, rise before the sun each morning and gets to work by 5, 7 days a week.
That's the way it is.
He's a nuclear chemist whose passion is filling in the blanks at the upper reaches of the periodic table.
Pop quiz.
The chart of elements.
Number 44.
Ruthenium.
Oh, very good. 109.
Meitnerium.
Very good. 114.
Unnamed at this point. You're not going to trick me.
The trick, as Ken sees it, is to be the one to name 114, which he's been on a quest to discover for more than 2 decades.
We tend to call these things discovery experiments, but we're really producing them. It's an act of creation.
Creating them with atomic colliders, quantum calculation, and something passed on to him by his mentor, Dr. Glenn Seaborg.
He was a big believer in those little 35-millimeter slides, and he'd take a graduate student to run the projector for him.
One of those students was none other than Ken Moody. That's a younger Ken there. For 30 years, Ken has held on to this particular slide. Seaborg's map, a mythical place the elements of the periodic table inhabit. And it's here where our story begins.
Where uranium and thorium dwell, the end of the nuclei that exist in nature.
Number 92, uranium, is the last of the naturally occurring elements. This is as far as the stars got. But Glenn Seaborg thought he could pick up where the stars left off, actually creating elements, and he did. Marching up the periodic table, creating elements 94, 95, 96, 97, 98, 101, and 102. He won a Nobel Prize for his pioneering work and created more elements than any human ever had. And then he could go no further.
Even Seaborg ran out. The process by which he was making these, he had his whole large team by this point, that way of trying to add in more protons to a nucleus, that route finally dried up.
David Kaiser teaches the history of science at MIT.
What Seaborg had been able to do, and many colleagues by this point, was sort of go step by step, add in one new nucleus at a time by just going literally baby steps.
How exactly do you take baby steps? Let's start at the beginning. We'll take a trip and fly into an atom, past the electrons, into the nucleus. In a science where you never see what you're working with, a lot is left to the imagination. So first, let's meet some protons. For our purposes, represented by these guys.
All positively charged, and we all remember from science class in high school that 2 positive charges repel one another.
With this repulsion, how do any of the elements stay together?
The protons feel a different sort of force as well at the same time. It's a different origin, a different type of force between them, and that's a specifically nuclear force. It's called the strong force.
We'll show this as a bungee cord.
And that really is how this force behaves. If they try to pull apart, it'll pull them back together. It's an attractive, coming together sort of force. But, like a bungee cord, it only works over a certain distance. If you try to stretch it too far, that cord will break.
That repulsive force wins.
And that's where this guy comes in.
Hello.
He is a neutron.
I went to school with an awful lot of neutrons. This is a fellow who comes equipped with bungee cords like the proton.
But unlike the proton, he has no charge, no inclination to push anything away. He just sort of sits there, neutrally. His bungee cord does the work. So, throw him in between a pair of struggling protons, hook up his bungee too.
The neutron provides some remediation of the hostility of the protons, and they can survive.
Up to a point. By the time he got to element 102 with 102 protons in the nucleus, Seaborg began having problems.
Even if you add in more bungees, they might keep this cluster together here, they might keep that cluster together there, but keeping the whole big thing together, that no longer is going to work. The pushing away force starts to win.
And there was another problem. Seaborg found the more protons he added, the shorter the atom survived. From billions of years down to thousands, days, hours, minutes.
Even much less. Sometimes thousandths of a second. If you're lucky, often it's millionths of a second. So these things will fall apart literally in less than a blink of an eye.
Seaborg came to see himself surrounded by a cruel and inhospitable ocean that tore his atoms apart. He called it a sea of instability.
The sea that they didn't know if they could cross or not. That's what was inspiring and really teasing or pushing Seaborg, and in fact many of his students and colleagues, to see could they go beyond this end of the known world? Could they go beyond where this peninsula seemed to stop?